So I'm going to say a few things about, so one of our topics in this year's thing is non-equilibrium dynamics, and that's the part I'm going to talk about. And I'm going to particularly focus on many-body quantum dynamics, which there's a bunch of different things there, since that's the area that in the subject that I'm currently interested in. And I'm going to draw a landscape, kind of like Jörg did, but this is going to be more like a phase diagram, although it's a rather informal phase diagram. So let me just sort of lay out a big picture of the class of questions that are there, at least some set of class of questions that are there in thinking about many-body quantum dynamics, right? So actually, let me just say, so we got many bodies. That means many degrees of freedom. Quantum, so that means unitary time evolution. So quantum dynamics. Okay. Means unitary time evolution. And in particular, I'm interested in the case where this is either given by a local Hamiltonian or a unitary operator. It doesn't have to be a Hamiltonian dynamics. It could be some sort of Floquet dynamics. But I'm interested in the issue of it being where the interactions are short range in real space. So there is a real space. There are many degrees of freedom spread out in real space, and the interactions are short range. Okay, I'll try. So let me just lay out my map here, but there won't be any mountains. So I wanted to put interactions on the vertical axis, and I wanted to put, let me write it this way, quenched randomness on the horizontal axis, and we're going to keep it quenched. I'm not going to ask the question about that interesting question that Jörg brought up of what if we let this stuff move. Okay, so in this picture here we've got, okay, so this corner here, what's this? This is free particles. Right? No potential. Let's say the system's otherwise translationally invariant, so that and there's no interaction. So this is simple. Okay. And then along here, well, actually, let me not draw a sharp boundary, but if we have no interactions, we're really talking about the single particle problem. And so over here on the axis, we have at strong enough randomness, we have single particle localization, Anderson localization, about which quite a bit is known, and many things have even been proven if you go far enough out this axis, right? And then in this intermediate regime here, at least if you're in 3 dimensions or more, and I guess it can be true to some extent in 2 dimensions, you have a regime of where the dynamics is not localized, but instead is diffusion. And as far as I understand this problem here of making that statement anything like rigorous is a big challenge, which is still there. Jörg sort of brought it up in saying, right, if you could prove this, you could probably prove Ohm's law for that system and things like that. So there's certainly a big challenge already here on this axis, which is to understand how you get from this simple limit to this sort of simple limit. We can maybe say this limit of single particle localization, we could maybe call that simple now, if you don't mind, Tom and Jörg. It wasn't simple before, but I think it's pretty well understood now. Okay, so that's right. And then we heard, so if we go up from here, we have this, which I've talked about and John talked about, Manybody localization, where we have both interactions and the quint-randomness. And we have this nice result now in 1D from Embry and Spencer. Oh, you're not going to be on the paper? Oh, he resigned from the paper. I don't know. What does this mean, John?
I was holding back.
Okay. When are we going to see the paper? Monday.
12 a.m.
It'll be on the, 12 a.m.
Or whatever.
It'll be on the archive on Monday. Okay. Okay, good. In the physics section or just in the math section? I hope cross-listed. Good, good. Yeah. Okay. Now, what we understand as theoretical physicists about this, there's nothing special about 1D. There seems to be a technical barrier, which means that what John did here in 1D does not readily generalize to, say, 2D or 3D dimensions, higher dimensional space. So that's, I think, an interesting point. So, D greater than 1. I think there's a challenge there, and given that this result is available now, and there's no reason to believe that the physics is significantly different in the higher dimensions, I think that's an interesting challenge there, and maybe in the not too distant future, someone will make some progress on that, and that would be nice. Now we can leave this simple point turning on interactions, and there are a certain, of course, there's not just one way to turn on the interaction, so I really need a bigger space, but let me just put a special, there is a special case here, which is integrable systems, where they're interacting, but yet still solvable in some way. Beta ansatz solvable, or something like this. And so this transition from here to here, there's a lot known about them. So in some sense, this going from here to here, this is fairly well understood territory. Of course, I'm sure there's lots of open questions there. But then if you turn on more generic interactions, or, for interactions to sort of simply give an integrable system, that's usually only in one dimension, right? Well, it's just a crossover, right? Well, actually, no. In some models, there's a line of fixed points here, right? If you're talking about some Luttinger liquids or something, right? And so there's a whole bunch of structure over here, but I think it's in different cases. But that's sort of not what I want to. I'm not saying there's not nice problems to work on there. I'm just saying that's not what I'm going to talk about today.
Aren't you also going to explain that even in this region, you have, even if your particles are just sort of weakly interacting,
Right.
you can have phenomena which is very different from the integrable system.
Yeah, right. No, I want to move away from these two special cases. Is that what you're saying?
Yeah.
Right. Which isn't necessarily due to randomness.
Right.
It could be due to interactions, but I'm going to put it a little bit off the axis here. So if I'm a little bit off the axis here, it doesn't necessarily mean the randomness is important, right? Okay. And so I'm going to show that here. So these are the right. Yeah, well, your artistic skills are superior to mine. You tried to draw a three-dimensional picture with a little bit of success, but I'm not going to even attempt. So there's this region here of systems that, I guess, obey the zeroth law at long times. Systems that, well, yeah, go to local thermal equilibrium without an infinite number of conserved densities, just some small number like energy, particle number, maybe momentum or things like this. And usually in this region, at least some of those quantities are moving diffusively. You could have some propagating modes like sound modes and things as well. But like in a gas, I'm speaking to you by ballistic modes, but temperature moves in the gas, or there's another mode which moves diffusively, which carries most of the heat, well, ignoring the convection. And very interesting questions are understanding moving away either from this limit or these limits and crossing over into this behavior. So as far as we understand, for systems in the thermodynamic limit, this is a crossover. It's not like integrability survives to any non-zero threshold, although it would be interesting if there was some real intermediate different state. But and these things here, exactly what could be said about how you go from. But this would be, well, one approach to this is what people call quantum Boltzmann equations, or quantum Boltzmann. But there may be other approaches, and I think this is a area. It's an area of interest, and it seems like statements about how this crossover happens, at least some limited statements about how this crossover happens, seems like they should be and maybe already are said and proven in a mathematically proper way. I don't know if anybody has anything to add about that. It's not something I know a lot about, but I know it's something that the people who are thinking about integrability and thermalization in physics are arguing about these questions. And there's experiments exploring this switchover. You make an integrable system, some 1D Bose gas, which is Lieb-Lininger integrable, but then either think about the corrections to the approximations you had to make it to map it onto the Lieb-Lininger model, or intentionally add more terms to the experimental system and try to study it crossing over to something that equilibrates as opposed to remaining integrable and not really thermally equilibrating. So I think these are interesting questions, and it sort of seems like there should be at least some aspects of these that one could really prove some things about. So that's just now and then thermalization itself. This diffusion is hard. This is hard because you're talking about coherent motion of a single particle in a random potential. Whereas up here, we might have many particles scattering off of each other, something which, there's no, we could have no randomness, right? Is that a regime where being able to show some sort of ergodicity or could be easier than having to deal with the static random potential? I don't know. So that's, there's probably showing thermalization in any realistic dynamics is a hard problem, but I wonder, the essential physics of it in some sense is simple, right? So is there something there to work on?
First thing to look at would be the non-random.
Yeah, no, I think this is, well, I don't know. That's a question. Is the randomness a help or a hindrance? And given that this problem is hard, I'm saying perhaps the randomness is a hindrance to doing, I don't know. Again,
I think it's maybe even harder, but
yeah. Are there, there's classical problems where various forms of ergodicity are proven, right? Right?
that's pretty hard though.
Yeah, right. So, can one build off of any, well, anyways, this is just, I'm just sort of saying where in this landscape are there challenges which, yeah, and then of course there's this, one of my big interests is this phase transition here, but that's I think very hard.
Can you comment about what you speculate will happen with this transition?
Well, it's a version of the mobility edge in Anderson localization, right? Of course, and that's why I don't want to even suggest it as a problem, because even this transition down here is too hard, right? And this is certainly harder. So I don't think that, since this is due to the disorder, right? There's no reason to think the Manybody problem could be in any way easier or more accessible than the single particle problem, right? The thermalization, you could get rid of the disorder, and is this an advantage? I don't know, probably not, but it's sort of not manifestly harder than this problem. It's just a different problem, right? Whereas this one here, this transition here, it's a mobility edge like this one is from diffusion to localization.
Do you think there's any kind of, is it possible that there's some kind of mean field structure that sits up there that wouldn't be field down below?
Yeah, well, that's being looked at, right. So in fact, guy I'm working with has a, I think, ill thought out, although it may be better thought out than I understand, mean field description of approaching from this side onto that transition.
So that might
By-
be a dimension-independent kind of structure. that could
Yeah,
work.
so the picture that's being explored is you have a system, you have a subsystem which has got a bunch of many states inside the subsystem. We're on the thermal side of the phase transition. So ultimately, the rest of the system is a bath for this subsystem, right? And then you ask, okay, I have a bath with some properties. I couple my system to it. It's got a bunch of spectral lines. They get broadened by coupling to the bath, and then have the bath have the same spectral properties as the system, so you make a mean field theory. So sort of ask, what spectral properties can I give the bath and couple it to my system so that the lines in the system broaden into something that looks just like what the bath was, so that it's just, that's what you do in a mean field theory. So this is what people call a dynamical mean field theory, which is being done quite a bit, but more for ground states in strongly correlated quantum systems. And so there, there's an effort in that direction. Because the idea would be a mean field approach to a problem is that you say your subsystem is interacting with another subsystem right nearby, which is identical to it, and you solve self-consistently, right? This subsystem interacting with all its nearby subsystems has the exact same properties as these subsystems had that you put in to start the calculation, and you close that loop with a self-consistency. Exactly what you need to do when you're talking about the bath properties, it's not obvious how to formulate such a calculation, right? And that's why I'm not certain that this,
Is there some simple example?
for dynamics.
Yeah, for this one.
Well, okay, so this has been worked out for the dynamical mean field theory, which is primarily applied to ground states, is well worked out. I don't know if I could reproduce it, but there's a big physics literature. The simplest version, you might just have one site, right? And then you have, in fact, one way of formally deriving dynamical mean field theory is to take your model, take it to infinite dimensions. The nice way of deriving mean field theories is to just give your system an infinite number of neighbors and having them be IID and uncorrelated, and that's a way to make a mean field theory. And so
I told one next time, so
but that's not going to work here. Just that simple picture isn't going to work here because we're talking about a quench random system, and this guy will have, each subsystem will have its own local spectrum with its own spectral lines, and if we average over many of them, we'll just get a continuum, right? And that's not what the neighborhood of this looks like, right? And so just naively following the usual prescription for mean field theories, which is to say give it an infinite number of neighbors and assume they're uncorrelated with each other, is clearly not appropriate in these systems with quench randomness, right? And so that's why this is, right. Now, I'm sort of, Tom said, is there any ideas, anything underway? Yeah, there is. Whether it's any good, I don't know. Whether it's going to lead to anything interesting, but does that make sense?
So a lot of this, when you're making these pictures, you're not talking about ground states in general.
No, right. Okay, so this is let me just say. High energy, meaning thermal state. When the system thermalizes, we're talking, when it thermalizes, it's, let's say, not equal to 0. Could be negative temperature, that's fine. I don't have no problem with negative temperature. So I don't want to say greater than 0. And it could be infinity temperature, that's fine. Just not 0. Neither 0 approach from above, nor 0 approach from below.
But does some of this picture also survive at 0 temperature?
Well, what thermalization means at 0, thermalization at 0 temperature is in some sense trivial.
Yeah.
Right. And one could, it wouldn't be 0 temperature, it would be 0 temperature. If we're talking dynamics, we can't be strictly in the ground state because then there's no dynamics, it's just static. So so what I'm talking about here is extensive energies above the ground state. So you can do the ground state plus order 1 or epsilon energy excitations and see transitions from localization to non-localized phases like superconductors or metals, if you have fermions, or and then I guess this would still be there. There would be localized, it would be an insulator, and this would be a metal or a superconductor or something like that, right? So there still is such a thing. Yeah.
So what do you mean
But I say that's a different thing than what I'm talking about here, really. The ground state's a different problem. Sorry.
What do you mean by saying that thermalization at 0 temperature is trivial?
Well, I like to define thermalization by saying the subsystems are in the same state that they would be at thermal equilibrium.
Yes.
And so if your system has a unique ground state and you're at 0 temperature, then there is just one state, and it is the thermal equilibrium state by definition, right? So that's all I mean. It's a trivial statement. Yeah. Of course, if you have ground state degeneracy.
Ground states are easy to understand.
Oh, no. It doesn't mean that ground states are easy to understand. It just, the issue of thermalization is that you're at an energy density where there are many, many states at that energy density, and many states which are way out of equilibrium at that energy density. But yet, if the system thermalizes at long times, it goes to states that, obey the zeroth law, which is a non-trivial thing. Except at zero temperature, where there is only one state, and it's in some sense, a certain sense, trivial. Not that ground states are trivial. It's that their dynamics, the dynamics of eigenstates of the Hamiltonian is trivial, because eigenstates have no dynamics. That's all I'm saying. Okay. And then I just wanted to say one more thing, which is perhaps slightly related to what Michael's going to say, although we'll see, which is another question, I think, there's more to be learned about, which is approximations to the, not necessarily many-body localization, just approximations to the many-body problem, right? So the many-body problem with a local Hamiltonian, it's in a state space, which is a product space, right? We have quantum degrees of freedom at each site, and they each have their own Hilbert space, and the Hilbert space of the many-body problem is the outer product of all those Hilbert spaces, or whatever the right words are. And so it has a certain structure, right? And I think I talked about this in my talk a few weeks ago. So for example, if we consider a spin model, right? So we've got real space, and then we've got, I'm going to call it Fock space. So real space might have n points each, and there's a spin at each point. Let's say it's a spin-a-half model. A bunch of interacting spin-a-halves. These are the simplest models to explore these issues in. So this has got n points, whereas Fock space, let's just choose a basis, spin up or down at each site. It's got 2 to the n points. Right? So these are a certain set of basis states of the many-body problem, right? And it's a hypercube. Right? They're basis states. Yeah, I'm not sure what the right words are. I don't know what the best words are for this, but what I mean is by the 2 to the n states, these are just different patterns of either up, down, right? You just choose a basis.
That is what's called 2 to the n dimensions. Complex dimensions of Fock space.
Right. Okay. So then there's the vector, the state space. Yeah, you weren't here when I gave this talk, so which is C to the 2 to the n, right? I'm talking about this space, which is a hypercube with 2 to the n points in an n-dimensional space. It's intermediate between this one and this one. This is 2 to the n-dimensional space. Here I'm talking. Well, okay. So I'm gonna. Whatever.
All right, we know what you're talking about.
Yeah. I'm not claiming to use the terminology that everybody else uses, right? But what I mean here is a set of basis states, right, which are in a hypercube, right? And so I can draw that here, right? And whatever my Hamiltonian is, I can view it as a single particle hopping on the corners of this hypercube, because it's going to have terms which are diagonal in this basis, and those will be the potential energies at the corners. And it'll have terms that are off diagonal in this basis, and those will be terms that hop a particle from one site to another on this hypercube. So whatever the many-body problem is, if it's got the right kind of discrete space so I can do this, it can be mapped onto a single particle problem in a high-dimensional, on a high-dimensional graph, right? And if this is n is very large, Of course, this hypercube does have a lot of loops, but most of the paths, don't have loops, right? The loops, in some sense, are, if you start wandering around on this graph, your chance of closing a loop very quickly, if it doesn't close quickly, its chance goes to 0. And so, again, you might approximate this with a beta lattice or a Cayley tree or a Erdős-Rényi random graph or something and take a large system. And that's what I mean by approximations to the many-body problem, right? And this has been discussed, and I think it's an interesting, but the many-body problem has a very special structure in that the Hamiltonian is a sum of terms associated with each direction on this graph, and this Hilbert space is really a product space, right? It's got a product structure.
And the randomness appears like.
And the randomness, right? There's not 2 to the n random variables going into the Hamiltonian. There's just n, right? And so the thing's got a lot of structure, right? And so I think an interesting question is what many-body problems. Okay, so we could take this and, sort of replace it with some tree, right? And some approximation to the problem, which is easier to work with, right? Of course, if you do it on a tree or an Erdős-Rényi random graph or something like that, it's often technically very much simpler than really doing this with all its structure. And the question is, what properties, and I think this is, what properties can we really say, would go from one to the other? When would this approximation be reasonable? For what problems, for what questions, and when not, right? And so I think that's this is an issue that's around. I don't know that anybody's really said very much about it, right? It's it's something I.
Mechanics, we know they're very close, right? If we look at.
Well, what question?
Well, phase transitions or something like that. The Ising model on these different systems. They're quite.
That's right. Yeah. Right. Exactly. Right. If we just put some spins on this graph and gave them some interactions and looked at the ferromagnetic transition, right? It would be the same universality class. It wouldn't matter. The loops, the small numbers of loops wouldn't matter. Exactly. That's the point, right? And so there will be models where you move it from this graph to this graph and take away the product structure, and it's not going to change the things you're interested in. And then there will be other questions and models where it really totally changes the physics, right? And I think there's a class of questions here that, because people are doing this, talking about this, there's a class of questions here which I don't think have really been, at least I'm not aware of, people focusing on it other than just, I make this approximation, as opposed to sort of asking, in more detail, what does this approximation really mean? When is it valid? These kinds of questions. Of course, for statistical mechanics problems, that kind of stuff is well understood. Right. But for a quantum dynamics problem, what can one do? Right? It seems like there might be some opportunities there for helpful contributions.
Like just none of those loops isn't so much the main issue. It's the n versus 2 to the n random variable.
Yeah. And the product structure of the state space. Yeah. So I'm gonna end there, and we can have some more discussion, or I can yield the floor to Michael.
Well, I was going to ask you some more questions.
Okay.
So could you formulate, in one of these examples? So you expect in 1D that there's a transition, right?
You're talking about
Yeah.
this many-body localization transition. Yeah. Right. Now, the numerical evidence for that is pretty nice. Well, no. Okay, so there's one transition, or maybe there's always a question, could there be some intermediate phase? right?
Could you be specific about the I think I know what the answer is, but I think it would be helpful if you could spell it out more explicitly. What the order parameters are for such a transition.
Yeah. Okay, so, and I think one could emphasize thermalization, one could emphasize localization,
Right.
and they're not obviously, as I would define them, they're not obviously, they're things which I guess they're exclusive, but you could have intermediate behavior, I think, okay? So for thermalization, the way I do thermalization, okay, so first of all, you could look at long time, or you could look at the exact eigenstates, and you look at subsystems, and you ask, is the subsystem in the state it would be at thermal equilibrium, either at long time or in an eigenstate?
So could you actually write down for
Write it out.
more
Write it out. Okay, fine.
what precisely that says? You can write
Okay.
down the Hamiltonian, which of course you explained to John and me, or whatever form Hamiltonian you like.
Let me try it without specifying the Hamiltonian and see if you're comfortable. See if people are comfortable.
Yes.
Okay. So there's so let me just do eigenstate thermalization because it's simpler in a certain sense. Okay, so you take your Hamiltonian of your full. Okay, so first of all, we have a closed system, many-body system, and we're going to take the thermodynamic limit after writing the equations. It has a Hamiltonian, so we actually have a sequence of Hamiltonians. And it has eigenstates, so we have a sequence of eigenstates as we take bigger and bigger systems, which have eigenenergies. So this is what we have for each size system, and we have such a sequence. Okay? And then we take the eigenstate. We take the trace over the rest of the system, right? So I have a subsystem I'm calling S, and S bar is all the other degrees of freedom outside of my subsystem. Okay? So this is what people call the reduced density matrix of subsystem S and eigenstate N. Right? So that's the reduced density matrix of subsystem S in eigenstate N.
I'm a little confused about this notation here, this trace.
This is a partial trace. Right, so this is a state on the Hilbert space of the full system, or this is actually a density operator on the full system, and then we take a partial trace, and so what remains is an operator on the subsystem, because we've traced out everything outside of the subsystem. Okay? And then eigenstate thermalization is this is equal to, in the limit, when we take the thermodynamic limit, trace over the complement, right. Let me just do it for something with a conserved energy and no other conservation laws. So that's, well, partition function to normalize the thing properly. So this is the equilibrium state of the full system in the Gibbs or the Boltzmann distribution. And this, and that would be beta sub n, right? And so this I would call rho sub s equilibrium at beta sub n. And beta sub n is the temperature of the full system that corresponds to this eigenenergy at equilibrium. Right? So this is eigenstate thermalization. The eigenstates are thermal, and it should be true for all finite subsystems. And it should be true for at least almost all eigenstates of the full system, and probably for all. But that's not clear whether it should be almost all or all. Right? And it might be true for the subsystems as well. We need almost all in order for equilibrium statistical mechanics to work for the long time behavior. Is that enough?
Well, we could ask for more, but...
Well, let's let Jörg ask for more.
So I suppose you want energy density to...
Yeah, right. So we take a limit, so the energy, so we take a limit so that the temperatures associated with the eigenstates goes to a limit,
Yeah.
right?
Now, why is it possible to be a little perverse and look at the sort of very exotic sequence of eigenstates that in the end produces the right energy density, but is selected in such a way that your hypothesis becomes wrong?
That would be very interesting if you could do that, because that would mean there are eigenstates which deviate significantly from this, right? And that's a question. That's a very interesting question, which we're exploring numerically. To what extent, if we take a system that we know certainly appears to thermalize, and we look at all the eigenstates, and we look for the worst actor, the one which deviates from this as much as possible in the finite side system we can diagonalize, and then see how those behave as we approach the thermodynamic limit, and they seem to converge, but it's just numerics.
So in fact, I have to finish my question. What's wrong about the idea that you take a little band of energy densities and you average over all eigenstates that have energy?
Well, that's just the microcanonical ensemble. That's trivially thermal.
I mean, that looks like a much safer conjecture.
Well,
you do a little
yeah, not only that, but it's true. Right. No, it's too weak a statement, right? That's just saying the microcanonical ensemble is fine.
That won't tell you really long time behavior.
It doesn't tell you about the dynamics.
Explain long time. You need
That'll be true in the many-body localized phase as well. It won't be able to tell. Okay, right. So yeah, so you weren't at my talk, so I advocate. Well, you were at my talk at Rutgers. Yes, right. So as you might remember, I advocate a new statistical mechanics, which is single eigenstate statistical mechanics, where instead of taking one of the traditional ensembles, you choose a single eigenstate of the Hamiltonian as your ensemble. And in that way of doing statistical mechanics, localization transitions are quite apparent, whereas they're not apparent in any of the other traditional statistical mechanical ensembles. So it's important to me to take one eigenstate. Yeah.
No, but I would say it like this. If you don't take an eigenstate, you take a little band of energy.
He said band of energy densities, right? Yeah. And that's horrible.
I understand.
But a band of energies is also horrible because the level spacing is exponentially small in the size of the system.
But that's like a little band of energy density.
Right. But then you lose all the interesting physics.
Well, that's exactly the point that I do not understand and do not believe.
Okay. Good. Good.
I agree with David.
Yeah. Somehow I've gotten the message across to him. But yeah, as you said in your talk. Yeah. Even though you were at the talk at Rutgers, somehow these messages didn't get across.
So
Yeah.
the
Yeah.
question as to whether
So anyways, this would be.
whether single eigenstates are of interest somehow in physics.
No, single eigenstates are of interest in physics because they are what gives the dynamics.
That's it.
They're not of interest because physical systems are in eigenstates. They're of interest as calculational tools for getting the dynamics. Yeah.
So my comment is.
And this ensemble I'm proposing is not a physical ensemble. It is a useful ensemble for studying physics, right? It doesn't represent an experimental system, neither does a microcanonical ensemble, right? Microcanonical ensemble there's no experiment that looks like a microcanonical ensemble, but yet it's a very useful device for both pedagogically and calculationally, right?
Maybe I can.
And this is another artificial but useful ensemble. Just like the wave function, it's just an artificial but useful construction, right?
There's a distinction between real time.
Or even the Hamiltonian, right? These are all just constructions which are useful, right?
That statement about how the single eigenstate can help you understand dynamics?
Can I make a?
I can elaborate on that, but Tom wants to.
I take learn about time dynamics, which is proportional to the width of that inverse of the width of that interval. And I lose everything else. Basically, I lose
Right.
Well, I mean, this is some kind of uncertainty relation.
Exactly.
That's fine, you see. But in the end, if I have a little band, I can make the width of this band ever smaller.
Yeah.
But I would never look at the single eigenfunction because
Right.
for
I
every
recommend it,
system
though. You should
size-
try. You should try, because I've really enjoyed doing it. And I think I've learned a lot from doing it.
But I think you're not distinguished by looking at, unless you make the band small compared to the size of the system, I mean exponentially small to the size of the system, you may lose the distinction between localization and extended states, for example.
Yeah.
But-
Yeah.
but-
Right.
but-
Right. No, this isn't the
Not
only.
evolution, but-
This is not the only way to make the distinction. I'm not claiming that. I'm just saying this is a way. You know,
Would you say us how?
you know, we could measure the thermal diffusivity here, right?
Let's talk about that for a second.
So we could just measure the thermal diffusivity here. Say it's a spin model, and you know there's some energy transport, so I could measure the thermal diffusivity.
Down for us too, or is that too
What, I want to write down a Kubo relation, or what do you? You're it's been a long time since my thesis exam. My thesis exam, it was Michael Fisher, David Merman, and Bob Richardson. And I'm sort of feeling like that. Right. So the thermal conductivity is, I'm not going to get the factors. So it's right. You look at the energy current. So the uniform energy current over the full system at time 0, correlate it with at time t, and then just expectation value of that, integrate. It's basically in some factors. Am I missing something? Well, that's what these brackets mean. Yeah, these brackets are whatever expectation value is appropriate here.
And what would that be?
Well, you can't do this calculation in the single eigenstate ensemble, right? So if you want to do this calculation, this is not the right ensemble. So if that's your point, I fully agree. Right. If you want to calculate this, you want to work in a different ensemble or just take an initial state, right? And you could just average, you know, this could be T1 plus T, you know, dt1, you know, one of them integrated from 0 to T, 1 over T, you know, just to sort of equal time average. So you could have some initial condition, or you could have some ensemble and take the average in there. But you're absolutely right. The single eigenstate ensemble that I'm proposing is no good for calculating this. The Kubo formula is not true in that ensemble. Yeah, the Kubo formula. Well, it's because, you know, rho, so the state of the system, we can write, if we have, so in the basis of the eigenstates of the Hamiltonian, rho of t has just trivial dynamics. So this is equal to rho of 0. This is in the Schrödinger picture. There might be a minus sign there. So this is the state of the system as a function of time, and all that happens is all its matrix elements just pick up these phase factors, and that's it. So the eigenstates make the dynamics, in some sense, trivial. Right. But that's just elementary quantum mechanics. I don't know. That is that.
Well,
Is that an answer to your question, or did I misunderstand your question?
Let me make the following hypothesis or guess that the single eigenstate ensemble is necessary if you want to probe time scales that are exponential in the size of the system.
Well, I'm not saying it's necessary. I would suspect almost anything you would want to calculate, you could calculate it by some other way,
But I mean,
right? So I'm just saying it's useful.
Time scales, or is there a range of time scales?
Well, when the system goes from localized to non-localized, the eigenstates change in their character, right? When you're in the thermal phase, if the eigenstate thermalization hypothesis is true, all the different single eigenstates look the same. Right? They all look thermal. Right? Whereas as soon as you cross this boundary, they're different. Right? So that can give you an order parameter. As soon as this stops being true, you can define an order parameter, which is how different are two eigenstates that are exactly the same energy on a subsystem. You know, by the norm, you know, basically, you know, I can do this same thing here. I can look at rho s n minus rho s n plus 1, just the next eigenstate over was exponentially close in energy. And then I can look at the norm of this, right? If the system thermalizes, this norm is 0, right? So this norm would go to 0 here. Whereas as soon as this stops being true, it becomes non-zero, right? And so there's a potential order parameter for non-thermalization and also, yeah, I guess, localization.
If I may chime in here, I think that's a very relevant point. Actually, that one which is not obvious is I think there is a new possibility that this transition may not coincide with the localization. This possibility.
Right. So it's a question of what you mean by localization. I was going to propose.
There may be another transition there.
You don't really mean that if this condition does hold, then the eigenstate is localized.
Localization is one mechanism for that, but there may be another.
Yeah, but it's not necessary.
No, I think it's more
Thermalized.
one can choose your definition of localization.
No.
And this is one possible definition of localization, and it might not be equivalent to other possible definitions of localization.
I'm actually talking about the previous form, about the limit when
This is about thermalization.
So that's what I'm saying. If this doesn't hold, does it necessarily mean that the eigenstate is localized, or is just not thermalized? No, if it doesn't hold. If it doesn't hold, does it mean that the eigenstate is localized, or it just means that it's not thermalized?
It's a question of what, like, I don't think in this context, when we're allowing the possibility of intermediate phases, that exactly what definitions you should be using are clear, right? And so I can't, there's a bunch of possible definitions. If there's just one transition, presumably all those definitions give the same transition. The possibilities for cases where there's an intermediate phase, I don't think it has been thought through that much in the many-body context, right? In the single particle context, it's been thought through, and in the case of on a tree, it's been thought through. But in terms of the just general many-body context,
Right. I think it's the possibility that these are different transitions is a fairly recent idea.
right?
And,
So you're saying even on the tree, it
not
hasn't?
been totally thought
Yeah,
through.
right. Even on the tree, right? You would.
But,
Yeah.
is that this order parameter?
My prejudice is there's one transition, but I think these are interesting questions to get straight.
Whether there is an interval.
Okay, so John has a limit of many-body localization where you could say you have many-body localization if there's a one-to-one map from all the eigenstates of the Hamiltonian to all the eigenstates of a sort of a nearby trivially localized Hamiltonian with just some unitary transformation, right? And so that's a very strong definition of many-body localization, which might break down before you get thermalization, right?
Is there a physical reason for looking at this thermalization order parameter, or is it more of a mathematical distinction?
Well, this we, no. Okay, so if this is true, it means the system, I would say this is a type of localization, right? Because what it means is you can have an initial condition where the system is stuck in a certain sense in a state set by the initial condition, right? I could start it in this state or in this state, and it remembers it forever, right? So it's localized in a certain sense, right?
It can be non-zero, but
Yep.
very, very small.
But there's a difference between 0 and non-zero, right? I don't think I should have to say that in this room, but
Very small.
it'll go to 0 presumably continuously as you approach the thermal state, right? If the thermal state exists and there's a phase boundary here, I would guess this quantity, somehow averaged over states, will go to 0 in some interesting way. Well, it's a random variable, right? Okay, it has a, we could, right? So we could say the probability of this, doesn't go to a delta function, right? Or, whatever, right?
You're talking about the probability, not in the randomness, right? In the non.
Well, there's also the different states. Right, there's the randomness and the states, right? And so this has some probability distribution, which, if the system thermalizes, goes to, whatever, all weight on 0 or near 0 or whatever, however is the right way to say it in this room.
So when you say you advocate using an eigenstates ensemble, you mean a randomly chosen eigenstates? Or you mean
Yeah, well, it's good to look at more than one, so you can do this. Yeah. Yeah.
have some group of maybe your band of eigenstates and you choose one of them from that.
Yeah, or maybe 2, so we can do this. Right? If I only have 1, I can't do this. Right? Yeah. But if I have 1, I can do this test in principle.
So, I guess you are a numerical guy.
Yeah, some of what I do is numerics, yeah.
Presumably, this is a criterion that is perhaps nice to implement numerically.
Yes, yeah, absolutely. That's why one reason I like it is because we've used it.
If you go to the lab, that is, so
No, it's not good in the lab.
So
No,
why
no.
is it possible to talk about this transition between, say, localization, thermalization, in terms of the thermal conductivity and various other conductivities? Why is it not possible?
It is possible.
Uh-huh.
Right. No,
But
there
you're
are
saying it's
there is a long list of distinctions between these two phases. So often I give a talk and I list 12 different properties that differ between the two phases.
now
And
the question is, what is computable in the end? Is this easier to compute than the thermal conductivity?
yeah, when you do exact localization, yeah. Right, because this is you just get the eigenstates and you do this. Yeah, so we do this. This is a very nice thing when you're doing exact localizations. But if you say in the lab, right, over here, I start the system out of equilibrium in some macroscopic way, leave it forever, it stays out of equilibrium. Here, it equilibrates, right? Yeah.
But so is kappa sufficient to capture that notion, or is it insufficient?
I mean, the problem I have is with stuff is exactly that it wipes out the equilibration, the relaxation times. Time doesn't appear anymore. But if I imagine from mathematics,
Okay, I'm sorry. Let me just say, it's a useful ensemble for certain purposes. For other purposes, it's useless. Okay? So if you want to calculate how long it takes the system to go to equilibrium,
Locally.
well, whatever, you need many eigenstates because that involves many eigenstates, right? Because it involves off-diagonal terms in the operator. Yes, right. No, I'm not saying it's a replacement for the other ensembles. It's just a different way of looking at statistical mechanics, and it allows one to see this phase transition in terms of just static quantities, right? You don't have to do it in the usual ensembles. If you want to see this phase transition, you have to explicitly study dynamics.
Presumably these two notions are
They're equivalent.
equivalent.
It's just two different ways of looking at the thing. Yeah. But then you look inside this phase and you see all sorts of phase transitions within the localized phase when the eigenstates change their properties, and get long-range order and things like this, right? So there's yeah. I think it's Michael's turn.